you've all heard the saying correlation is not causation. When people say that, they're using correlation loosely, like association or relationship. Or association is not causation. That's true. But now you've learned what a correlation is. It's the linear relationship between two continuous variables. But it's still true that a correlation does not imply causation. And we have to be very careful. How do you quantify this relationship between the length and the length and the weight of a bear? We said R equals 0.89. That's a tight relationship. What we can do with this correlation coefficient is hypothesis testing. Remember how hypothesis testing works. Statistics is backward. First, you postulate some hypothesis about where that parameter is. In this case, it's the Greek letter rho for the correlation coefficient. And we're going to assume, like most of the time, that nothing's going on. So our null hypothesis is going to be that rho is 0. And remember what that is? That's just a cloud or a blob of points. The alternative is going to be not the null. So in other words, there is a correlation. There's something going on. Now, for the mechanics of this test, it's not important for you to know the details, but we have a degrees of freedom. We're trying to estimate a relationship, a line. And in order to draw a line, you need 2 points. So what we do is we take 2 of our points and we say, okay, let's start with this bear and that bear. And we'll try to draw some sort of line. And then we'll use all those other points to sort of see where that line is. Now, the T statistic can be used to determine if this relationship is statistically significant or not. It turns out that if you use this formula, you take your correlation coefficient, you take your sample size, and in the denominator, you see the correlation coefficient again, you can get the T statistic. And that T statistic can then be used to generate a p-value. Remember the probability of a p-value, the probability of observing a test statistic of a given magnitude or larger if the null hypothesis is true. So the null hypothesis would be, hey, R is 0. And if R is 0, look at this formula. If R is 0, what is 0 times anything at all? Well, it's 0. So if the null is true, we would expect to get a T statistic somewhere around 0. What we'll do is take our data, calculate T, and then plot it out. Maybe we get something like 1.4. I'm just making numbers up. We'll say, what's the probability of getting 1.4 if there's nothing going on? Color in the area over there. Do a two-tail, color in the area over there. How much virtual ink did I use? Well, that's my p-value. If it's less than alpha, that critical value, then we reject the null. Let's try it for these bears data. Here, if you want to crank this through in Excel, you could do something like that. In Stata, to run this, we use the code PW_CORE, which stands for pairwise correlation. You list your 2 variables. And as you know in Stata, when you put in this little comma, then that indicates that we're going to give some options. And the option we want to use here is SIG. So what we get in the output, it's a little confusing, but what we get in the output is there's our number, there's our R equals 0.89. And then because we said SIG, there's our p-value. P equals 0.0025. If we're running with an alpha level of 0.05, then hey, it's statistically significant. There is, well, let's see this. How do we summarize this in a sentence? There is a significant and a positive correlation between the weight and the length of the bears. Say the name of the test. You have the statistic, right? That's the magnitude and the directionality. Always say that. And then the p-value. Now, we're going to see that in order to really use a correlation, we have to make sure our data are normally distributed, because we're using means, and the mean has to make sense for each individual variable if it's going to make sense for the linear relationship between the two things. Now, 0.89, is that high? Is that strong? Well, you can find any rule of thumb about what's high, what's strong, what's a relationship. Hey, as a rule of thumb, don't trust rule of thumbs. They're just guidelines. You might find a table like this. If your correlations between these numbers, it's small, it's medium, and large. But it really depends. It really depends on your field. If you're a physicist and your correlation isn't like 1, you suck at physics. That's not a law of nature. But if you're an economist, a correlation of 0.4 might be strong enough for you to uncover some truth about the way people behave. But Tybor, even if it's statistically significant, what do we do? If it's significant, doesn't it mean it's important? Well, think about this for a second. Here's our formula. In this formula, the T statistic is driven by two things. How strong is the correlation? And what is the sample size? Now, remember, as T goes up, what happens to P? Well, as T goes up, remember, here's the distribution of T if the null is true. As T goes up, you're moving further and further here, and your p-value is getting smaller and smaller. As T goes up, P goes down. Now, what I'm about to tell you is a little bit disturbing. Some students don't like to hear this, but think about this for a second. If you want to get a small p-value, what do you need to do? You need to get a high T statistic. And how do you get a high T statistic? Well, all you need to do is increase your N, increase your sample size. And how do you increase your sample size? I'm going to draw a symbol in the top corner of the screen. This is how you increase your sample size. So it's very interesting that statistical significance can be driven by your N. I'll show you an example. You see this picture right here? This is a correlation of 0.15. And if you look at those data, let's say this, I'm telling you, this is the relationship between how much cholesterol you eat and how your, blood pressure changes. You would say, I'm not really convinced by that picture. It's not that strong of a relationship. But check this out. I'm going to show you some fake studies with a correlation of 0.15. Each of these dots here is a study. Here's a study right here. And it's a sample size of like 50. The correlation is 0.15, and you see that my p-value is 0.4. Now, if I increase my sample size, if I have a sample size of, say, 800, even when my correlation is very weak, 0.15, look what my p-value is. I have this red line on here. That's my 0.05 level for p-value. So we have a little bit of tension here in that we need to have a big enough sample size so that we can believe our estimate. But as the sample size increases, we're making our p-value go down. We're almost like buying statistical significance. So what do? Well, you look and you need to think about, is it clinically relevant? Here are a couple examples of people getting the correlation is not causation wrong. What if you conclude the weight and the length of the bears correlate significantly? Well, we forgot the directionality. We need to say the directionality. What if we conclude something like this? Higher length, bigger frame, more muscle. But this is way too much detail to describe a bunch of dots that I just drew. The most important thing when you get data is to look at your data. We can look for extreme values. We can look for trends. We can see if things are linear. Here's a very famous set of graphs. And for each of these graphs, the correlation coefficient is the same. Let's say the correlation coefficient is 0.8. Now, your mental image of a correlation of 0.8 is something like this. But you can also get a 0.8. Look at this one here in the corner. This is a correlation of 0.8. But the correlation is driven completely by this dude right here. If you took that dude out, what's the correlation? Well, this is a blob. It's probably something around 0. You don't want to make a statement based on one observation. Now, if these were real data, you would look very closely. Why is this person's X value so high? Why is their Y value so high? Maybe it's a typo. Maybe they measured the wrong units. You look really closely at this person. Now, some students say, I have an outlier, throw it out. No, when you have an outlier, you look at it very closely. Thomas Kuhn said, from anomaly commences discovery. You have to investigate this point and figure out what's going on. This situation right here, we have another weird point. If this person's not in here, what's the relationship? It's a perfect linear relationship. We found something really interesting, maybe a new law of nature, but we got to explain what's going on with that guy. Now, I hope that this is some sort of measurement error. Hope I can explain this away. Look at what's going on here in 5. This example here. The correlation is 0.8, but that correlation is really driven by, it looks like there's 2 separate populations. And within each population, within this group here, what's the correlation? Doesn't look strong at all. What's in this group here? Doesn't look strong at all. We have some confounding variable or some third variable which is driving this association. Same deal we see here in this bottom corner, number 8. If you look at each group, the correlation in each group is not 0.8. In fact, the correlation in each group might be negative. How about number 7 here? What's going on here? If I tell Stata, hey, calculate the correlation, it'll say 0.8. But that's the linear association between 2 variables. And even my kids would come here, connect the dots and say, Dad, that's not a line, that's a curve. Fit the model that fits the data, right? And let's look at this one here, number 4. What's going on? The correlation is 0.8. But when you look at the data, what do you notice? Well, looks like there's 2 distinct groups here. It looks like in this group, the correlation is 1 with kind of a shallow slope. In this group, the correlation is 1 with kind of a steep slope. This is an important concept of effect modification, which you'll study in epi and which we'll do later on in the semester, that the effect in each group is different. So the take home here, always look at your data and be very careful not to imply causality when we're just looking at a bunch of points and trying to describe the relationship between them.